Well, hello there, everybody. Welcome to SkyTour LiveStream for July 27th, 2020. And what better way to start the evening by showing us the beautiful green coma of Comet NEOWISE. We've actually been so lucky. It's such a successful evening and what we call an apparition of this comet. It's just beautiful. So I hope you guys really enjoy this. And Bobby Bird just says, no sound. That's on your end. I'm pumping out sound. So you can certainly hear it if you turn on your speakers or something. But just to be safe, if you don't hear me, say so. You will know. But if you can hear me, just let me know that you can hear me. Okay? That way Bobby will know it's him. Because sound is going out. And hello, everybody. And I'm just going to turn off my fan because it's a little loud. Yeah, sound is good. See, people here. So see that, Bobby? It's you. Your speakers are... There you go. See, now he figured it out. So hi, guys. Nice to see you. Taylor Lopez, hello. That's a new name. We haven't seen you around. Thanks for coming out. And we have new faces all the time. Bob Harless is a newer face, and he's here. Cleo, he's been here the other day. Cleo Catra, how are you? Thank you for coming along. We're actually looking at the comet. You can see this beautiful comet right here. You can see this beautiful, this is the coma we talk about, and this is the tail of the comet. It's getting shorter because it's getting farther away. And by the way, before we get too far along, I just want to make sure everybody knows and appreciates that Daryl Mason is here with us. Hi, Daryl.
Hi, Mark. Ta-da, everybody.
Ta-da! Daryl's here, guys. Yeah, Daryl figured he would join us to check out this comet. It really is really pretty, and we like to explore the comet. There's no doubt about it. We have a good time. All right, so we got the coma, the comet right here. This is that green thing you see right here. That is probably right there. That is probably about 8 to maybe about 8 Earth diameters in size. That's huge, okay? But there's only a few molecules every cubic centimeter. There's not a whole lot in there compared to air. Air has many billions of times the molecules in the same cubic centimeter. But the comet is what's more what we call rarefied. The gas is very sparse in there. But from far away, millions of miles, like this is, it looks like it's pretty dense. Okay, this tail is even thinner. This gossamer tail that extends behind it and it goes out behind the comet. So we're looking at a beautiful apparition of Comet NEOWISE. This is getting along to be one of the last times we start focusing on NEOWISE, and we're going to move on to the summertime sky, and it should be a pretty time. But the reason we're doing so many of NEOWISE is, number one, because we can, and number two, because this is the brightest comet to come along in 23 years. So you'll be sad if there wasn't enough coverage of it. Eventually you might be sad. So this is a photo that we just took just now in the observatory scope, and this is the live view of the observatory scope right here. You can see the telescope right in this lower right corner. That's a live view into the dome right here. All right, and I know it doesn't, you can't really tell what's going on in there too well, but maybe I can just show you real quick so we have an idea. Okay, this is the back end of the telescope right here. This is a camera. This is up here. This is another camera that's on the scope. Up on top, above all that, is a guiding system, which you can see that light right there. That little light is actually the indicator that says that this guiding system has locked onto a star to guide with. And then this is the mount right here. This guy right here is when the telescope parks itself. And that's a little motor right there that I put on. This guy will close the hatch, basically, of the telescope and close it down. So once we're in Arizona with this setup, this exact setup's going to Arizona. and we're replacing it with another setup right on the same pier here. When this happens and this closes up, we can then close the roof. And if you look in the chat, you'll see that Marianne Robb is here, as is Tara D. Tara and Marianne are very helpful in helping to get the observatory along. Marianne is absolutely amazing, and she is doing some, I should say, just legwork that is, I don't know, her legs are going to be like 15 times the size of Popeye's. Okay, she's going back and forth to the different contractors to try and help us out, because she also believes in SkyTour LiveStream and wants to see it get propagated out there. And so to that end, all I can say is I will probably never be able to thank the people that have helped me on SkyTour LiveStream enough. So I'll probably be doing it for some years to come. So I just want people to understand that, Marianne in chat, if you're going to be nice to anyone, you darn well better be nice to her. Now, it doesn't matter that she's a police officer and can tase you, okay? It just matters that she has really given of her time, and I would like her recognized publicly for that, and I'm kind of giving that to her now.
Yeah.
And Tara's work will be evident potentially, and we're thinking about it on the observatory itself, because Tara is, of course, for those that know, is an amazing artist, and she has offered to actually paint the observatory with a desert mural of some sort on the outside, so that the observatory will have not only its logo on it, but it'll also have some interesting desert theme associated with it. And I have some ideas, Tara, which I didn't tell you about. I did talk to her today, but I didn't tell her about that. But I'll pass it on to you, okay? But if Marianne has some ideas, then I will, of course, listen to her as well. So what we're doing here tonight is we're going to be looking at NEOWISE, and the moon is out. We have a first quarter moon, and that's evident when we take photos that are longer exposures. This bluish background you see here in this second wide field view, this is actually a view that is got some light leakage in it from the moon. All right, but if we were to take, say, this is a 1000 ISO 8-second picture, photo that we took. Let's go to 13 seconds at 1000 ISO and take a picture. And now, while that's taking a picture, we can head on over to our other location, and with the other main telescope, and we can actually look here and say, let's take a picture here. We're going to put this up to about 3200, and we're going to do a 25-second shot of this. All right, and the other camera system has what we call a mechanical shutter, and it just happens to be the way that particular camera was built. The one that's taking these pictures, there's no moving parts. And that's what you want with an astronomical camera. The other camera that's doing the wide angle stuff, I've just fitted to the telescope for now. And we're going to get another camera at some point that also doesn't make any noise or make any motion, doesn't have any moving parts, that will allow us to do wide angle shots of the night sky. And I'm considering, and this, Daryl, is one thing that you might be interested in, I'm considering an astronomical camera of sorts that you would normally put through the eyepiece. What I put through the eyepiece is actually a digital single lens reflex camera, one like you hold up to your face and has a lens on the front that can come off. But instead of the lens on the front that comes off, it's a telescope on the front. And that is one that actually is just what I think we would use. So let's do this photo here. 25 seconds. What's that?
I said, heck yeah.
Yeah. So I will take a 25-second shot here at 3200. And meanwhile, let's go see our other shot. All right. This is the shot that we just took. This is 13 seconds at 1000. You can see the comet's tail going up there. Let's actually increase this. I think we can get away with that. Let's go up to, let's do a 25-second shot at 3200 for this one as well. Okay, and here we go. As you can imagine, I love controlling cameras electronically and from remote access. That's probably the best way to do things. Okay, and for me anyway, because I do believe that this is something that we want to use in the future. As I move this, by the way, this is a way to actually see the tail very well. If I move this, you'll actually see if you kind of just sort of not even follow it along, but let your eye just stay over here as I move it around. Okay, you'll see, and it's hard not to track, but if you do, you'll see there's like a fan-shaped tail here. All right, the tail is changing day to day, day by day. All right, and there's also a gas tail that's going out this way, but we can't really see that yet. It's really not dark enough, and it's hard to see with the moonlight. But we will do so. And here's another version of it. All right, and this is at 3200. And there's a satellite, of course, going through the image. We tend to find those quite a bit in our images, you know.
More and more.
More and more, as you said yesterday too, right? Or the day before. More and more, that's right. Okay, so here you can see as I move it back and forth, you can see where the tail looks like this big fan now sticking out off the back of the comet. And that's not unexpected, because as the comet is going through its orbit, some of the particles are being deposited in the orbit and are being left behind and lag behind the comet as it moves on out past. And it's the solar wind, the light pressure, basically, that is pushing this dust beyond the cometary nucleus and sending it out into space. Now, with the ion tail, which is blue, and they're ionized gases, that's a blue tail that goes straight back from where the sun is. And it goes straight back. It doesn't have any it doesn't have any bias. It doesn't have anything that causes it to curve. It's really an effect of the intense ultraviolet light from the sun. So it goes straight back from the sun, all right, it's in the opposite direction of the sun. And the dust tail, though, is particles. And those lag behind a little bit, and that's why they drag out a little bit, and that's why they make kind of like this fan shape here. As you can see, right, it starts up there, and it goes out here. Actually, that's really different from yesterday, Daryl, or the night before.
Yes, it is.
It's much different, you know. So it's pretty cool. Let's go look at our... Oh, sorry, go ahead.
Looks like it's getting smaller.
It is, yeah.
Moving away from us.
All right, this is our other view that we took this photo earlier, just a moment ago, actually. And you can see in this one, you can actually see... Oh, this is a really pretty shot, you know. You can see the coma in there, and it's really, really bright looking. And it really makes it look like it's dense in there, but it really isn't dense at all. And it's actually a very, very low density. If you flew through that with a spacecraft, you might not even see any particles. The only way I know you wouldn't see any, but if you were actually to take a long time exposure, that's the only time that you would actually see these jets escaping from the surface of the comet. See, think of a surface of a comet or the interior of the comet as like a spongy collection of voids, and voids being empty areas. So you have this conglomeration of material that all piles on at the beginning of the solar system, and it's cemented by these different ices. And what's trapped in there is not air, okay? What's trapped in there is just gases that might have been frozen out of interstellar space. Now, when those gases get trapped inside the comet, and you think of the comet as being one gigantic spongy mass overall, in other words, low density, then what you'll see is that as the sunlight hits that stuff, then the outer areas of the comet will warm up. And as they warm up, little openings will occur, and the solar heating is now heating voids, areas inside, which will release gases. As those areas start to melt under the surface, and those will release gases that build up and build up and build up, and then push, they'll shoot through the surface every now and then. And comets will make these jets in all directions, you know, that are on the side facing the sun. On the side not facing the sun, then you may not have that happen, but you got to keep in mind that comets will do this. They'll rotate. Okay, this is, I showed you this the other night. This is Churyumov Grusimenko. It's a digital model that I 3D printed of that comet that the Rosetta spacecraft went to. And this rotated this way in space. So whatever side was facing the sun, if it was like toward you at the camera at this end, then that side would be heated differentially from the other side. And this would happen all the time as this thing would rotate. And as it rotated, we'd get different gas jets coming out. And that's what caused that comet to also outgas, and there's images of this outgassing taken by the Rosetta spacecraft just 8 miles from the nucleus. And you got to look these up. It is really, really something to look at these pictures. Really stunning. Really, really stunning. And I'm just going to check to see if I asked if Amanda wanted to come in earlier, and she hasn't responded yet. So I'm assuming that she's not around. If she comes in, then someone let me know, and I will say it in all caps because that's kind of what draws my attention. And then I'll bring her in. All right? Because I did invite her. And, as Daryl says, everything's better with Amanda.
Yep.
Yeah.
I say that all the time.
You do indeed. Yeah.
If I see her, I'll let you know.
Okay. Thank you. So, this is the comet as of now. I was thinking we could also, do a little looking at the moon. Incidentally, the coordinates for the comet were right on the money tonight. The other night when we did it, we would go to where the comet was supposed to be, and it wasn't there. So I think that the comet coordinates on the skylive.com were actually incorrect at that point. And I don't know why, but I went to those exact coordinates last night, and I didn't see anything. Nothing was there. And I had to hunt for it, as you guys remember. And I did. I found it, but, we basically, I don't want to have to hunt for it anymore. That's not a nice thing to do. You don't make your audience wait, right, while you're hunting for things. That's not fair. Not fair to you guys. So that said, we're going to make sure that we don't have to do that anymore. So tonight what I did was I actually went to the coordinates just a few minutes ago, and they were there. If you can imagine when I say coordinates, what do I mean coordinates? In astronomy, we have coordinate systems, ways to map stuff onto the sky that we want to find. And the way we do it is we extend the Earth's latitude and longitude lines out into space. So the equator on the Earth becomes the celestial equator out in space. Latitude lines, which are they start at 0 degrees at the equator and go 10, 20, 30, 40, all the way up to 90 at the pole. Okay, those are extended out into space, and those become what we call declination coordinates. We change the name, but it still means the same thing. Okay, and then from left to right, because the sky rotates at a certain rate per hour, we divide the rotation rate into 24 segments for 24 hours. And that rotation lines, we call that right ascension. Okay, and don't worry about the names, but the thing that you want to keep in mind is that when I say coordinates, declination is given in degrees, just like latitude is given in degrees, okay? And right ascension, though, where we talk about longitude lines, we usually express that in, degrees, minutes, and seconds, east of Greenwich, west of Greenwich, depending on which side you are. That's Greenwich, England. But we talk about, in right ascension, we're using hours. 24 hours, like in the day, and the right ascension values go all the way around in one day because it's a one day, so 24 hours in a day. All right, and that's because the Earth is rotating as well, and as the Earth rotates, the stars will always be at the same right ascension. So what I'm saying is we extend these lines out into space, and they stay there. Meanwhile, the Earth rotates around inside. Okay, and that's how we find things. So when we give coordinates, for instance, this comet right here on the screen is at a coordinate of 11 hours, 49 minutes, and 33 seconds. and its declination is plus 35 degrees, 37 minutes, 15 seconds. So we have an hours, minutes, and seconds, and we have a degrees, minutes, and seconds. All right, and we can take a measurement of what we call the star time. It's called sidereal time, and that's the hours and minutes and seconds that are right over your head right now. That's the current sidereal time, and not many people actually use sidereal time all the time, I should say. We use it, but we only use it sort of in passing because we don't really need it. It was a great convention when it was created, but sidereal time is very important for any real-time activities with telescopes and objects like this, like comets, where this is changing moment to moment. We actually did the other night. We actually took several sequences of this object, and then I made a motion image of it over time, and you actually saw it moving against the stars. So we get to see the motion of the universe right in front of us. I think it's really cool. Daryl, I don't know if you wanted to talk about right ascension and declination. I mean, you typically explain very well a lot of these things, but that's your call if you want.
Oh, I was thinking I might confuse everybody by talking about yet another system.
Please do.
You sometimes hear us talk about azimuth and altitude.
Yeah.
That is fixed on the sky. It does not move with the stars. Azimuth starts at due north, and it moves from north to east and then on around the horizon. And that is measured in degrees from 0 to 360, or 0 again, when you come all the way back to north. Altitude is from 0 to 90 degrees, 0 altitude being at the horizon, and 90 degrees being at the zenith, straight overhead.
As I'm showing here.
Uh-huh.
Yeah.
And those are fixed. Those do not move with the sky.
Yep.
So you'll see, sometimes I've seen Mark in this Stellarium program there, it'll be displaying an alt-az mode, short for altitude and azimuth, and you will see the you'll see the sky objects shifting moment by moment across that grid.
Yeah,
and
actually,
that's when he's in alt-az mode.
Yeah, like I am right now. So if I were to go over to the comet, all right, let's go to this star where we're looking right here. Let's just go over to this star. We zoom in really far. All right, and now you see what's going on. The grid's not moving relative to your position on the Earth, but the Earth's rotating and the grid is going with it, which is what Daryl was telling you about before. This is alt-azimuth, and you look up here and you'll see the numbers are changing. Okay, now the right ascension and declination aren't changing because those are extensions of the coordinates of the star. What's changing, though, is the azimuth and the altitude, okay? And that is the thing that is measured as a local entity. As Daryl said, it doesn't change. For you, that 0 is still the horizon, 90 degrees is still directly overhead. But it's all relative. That help you out there?
I could say a little about sidereal time if you wanted to.
Yeah, sure, go ahead. Tell people about sidereal or star time, as we say.
As Mark said, sidereal time means star time. And I have discussed this, I have mentioned this in the past, that sidereal time being star time, interestingly, if you go out and you watch a certain star rise in the sky, and you note the time when it rises above the horizon, if you go out the next night, that star will have risen 4 minutes earlier. And the night after that, it will be up 4 minutes earlier again. If you do that for a week, it will be up about 28 minutes earlier, or let's round that off to half an hour. And if you do that every night for a month, you will see that star will be rising about 2 hours earlier than at the end of the month. Or, excuse me, at the end of the month, it'll be rising 2 hours earlier than at the beginning of the month. And if you multiply that by 12, 12 hours over the course of a year, you get 24 hours. And this is why the sky shifts night by night. This is why the constellations change and the seasons change. And this is why it takes a year for that star to wind back up where it was at the beginning of the year.
Yeah, that's excellent.
And that's star time.
Yeah, and if you think about it, why should the stars rise 4 minutes earlier every night? And
I know.
I know you do. Well, actually,
Yeah.
I'm not going to make people think about that, but I will. You can tell them if you want. I mean, you don't have to get too much into Earth's orbit, but I think that it's probably a good idea to say something about that. Yeah.
Oh, you just said it yourself.
I'm sorry.
That is the Earth's daily motion around the sun. We see the stars shift in the sky 4 minutes earlier every day as the Earth moves in its orbit around the sun over the course of a year. That 4 minutes every day times 365 plus days a year, they're not even numbers, which is why we have leap days every 4 years. Not every 4 years, but most 4 years. That's what does it work out to? 1,440 minutes a year, I think. 24 hours times 60, plus a little less than a quarter of a day to make one of our years. And it gets complicated, but that's why things are like they are.
Yeah, and this is not a class on star time and sidereal time. I can tell you this though. When I was getting my degree in astronomy, I really hated the boring classes on coordinate systems and stuff. Ugh, it's like I went into school knowing all that, and then when I started learning it, I was like, yeah, get to some good stuff. So I was impatient, but I did listen because there's a lot of things you do learn from understanding how the ancients viewed the globe to how we view the globe. And to the advantages we have with our instrumentation that they never had. So it's really quite fascinating to study the coordinate systems and how things have changed over the centuries.
Oh, yeah.
Yeah. That said, speaking of change over the centuries, I'm going to change something here in just a few minutes. I'm going to take a photo. We're going to go 30 seconds at 4,000 ISO. That's the sensitivity of the camera. Most cameras go at about 6,400. The camera we're using goes to 409,000. So it's quite extensive, but 409,000 doesn't really do too much for us. Okay, because it's really grainy. All right. So I'll take that picture. We'll let it go, and while it's going, I'm going to say hi to the folks that joined us. I see, hey, D. Smith, how are you? Terry Groff is here. Tara, I mentioned. Rascally Rabbit. Rascally Wabbit is here. Keith from P&K. Bob Harless, Papa Tom. Tim F. Hey, there he is. Woohoo. Marianne Robb, of course. And Daryl, you're here. How about that? Did you know you were here? Well, that's pretty cool. I'm glad you knew you were here. And Bobby Burgess is here. And I think I said hi to Trish, didn't I? Trish D, hi. And then DK is here. And let's see, here we go. There we go. All right. And let's do this. All right. Okay. Yeah, that's a pretty good indicator of what it's doing. And I said hi to Taylor Lopez, but hey, again, Cleocatra is here. I think I saw Susie Cat as well. Susie Cat from Scotland. And we have, let's see, who else did I saw somebody else that was here. Oh, Brandy is here. Hello, Brandy. Brandy, I hope that everything I sent you for information is helpful. You got to let me know. There's a lot more to say to help you out there. And she had asked me a couple of questions that I answered for her. And then I think that we have D. Smith is here. Yes, I saw that. And then they had their discussion about the police with Marianne, who was threatening to arrest everybody. Out of control. not really. And then for those that I missed, I will catch up with you. And I like to always pay personal attention to everybody that shows up here. And that's important. So, oh, and Keith says they're done. They were hazed out. I'm sorry to hear that, man. Sorry to hear that. Keith's P&K Space Imaging, you guys, most of you know. Some of you actually came from there to find us. That's the telescope that Paul runs down in Miami, that Keith manages through Pennsylvania. And they do all of the moon and planetary views. And they're tuned to doing that in just a magical, amazing way. So I think that that's really important, and I'm glad that they do that. We do the deep space objects like comets and nebula and so forth, and then Bill New York Skywatcher does the meteor showers and wide-angle views. Okay, I want to say, hey, there's Anahata 77. Hi there, Bonnie. How are you? It's nice to see you here. And you guys, you really make the world go round for me. I want to thank you for spending the time that you do out here. So here's Comet NEOWISE once again. Cleocat is being funny out there in the chat. So that looks pretty interesting. This is visible light, just so you know. This is a visible light shot. And as a visible light shot, we are noticing that we're noticing actually that our beautiful comet has some additional colors. Actually, it looks like it's a little dim right now. That could actually be some clouds. We do have some, and I probably should turn on the all sky cam. And Keith, you just reminded me. That's fantastic. Thank you. If you guys go to astroimaginglive.com, you will see this stream, Bill New York Skywatcher stream, and P&K Space Imaging stream all under one roof, and you can pick the one you want to go into and have some fun for a while, back out, and then find your way to the next stream. And it's popping in and out of all of our streams. So when we're live streaming, you can actually find us there, and we're just working out ways to make sure that those links to our streams are always updated. We want to make it happen automatically, so we're working on that. But yes, please enjoy astroimaginglive.com on us. All right, and you can hear all the same great stuff. I feel like it's a commercial. Hear all the same great stuff, but one-stop shop. Just go to astroimaginglive.com. That's astroimaginglive.com. It's something like 70s commercial or something. And I see that we're missing the comet in our view, and I suspect I know why. And I'm going to just do a 15-second shot at 5,000 and see if it's true that there's a cloud patch over the comet right now. We had some moving in, and so we have to be wary that there might be some. Okay. So this is a 15-second shot. Yep.
Let me know if you need some. I'll send clouds your way.
Yeah, well, Daryl, I really, really thank you for the idea. But no. How about no?
Okay.
Yeah, we're all set. We're all set with those. Thank you. So let's see here. We got. Yeah, you can see this star and that star over here are this star and that star, and the comet should be here. So why wasn't it? It wasn't because we have a thicker cloud bank coming in. It's blocking it out. See?
Oh no.
Yeah, but that's all right. I've got other things to look at. If we have to. Thank you, Keith. Keith says P&K Space Imaging says links are being updated as you speak. Thanks, man. Thank you very much for doing that. All right. So we got a few views of the comet tonight. I was actually, come on, go away. I was actually thinking that we might get clouded out earlier, and the fact that we didn't is a good thing. I'm really happy that we didn't get clouded out earlier, but I do know that it does happen. And we have to be wary and know that that is going to happen eventually. So right now we're going to do another 15-second shot to see if that cloud bank was thin or heavy. And I don't want to sound like Han Solo and say, we got bounced too close to a star or head right into a supernova. That would really end your trip real fast now, wouldn't it, kid? I kind of messed up that line a little bit, but you get the idea. Yeah. Okay, and now the cloud bank's moved a little bit more this way. You can see this area that was the sky is now being blocked. So what I have to do now is go do an assessment. But first, in order to do that, I'm going to do something else. I'm going to minimize this stuff, and I'm going to get us to look. I'm going to get to look at my Oculus. The Oculus is the thingish we want us. Okay, so we say get the camera. The camera has what? It says device not found. Oh, that's right. Yeah, I can't use it. I had to unplug it because I'm going to be packing it up to send it to Arizona. So that'll happen eventually. So I'll have to go look. But what I'll do in the interim here while we're waiting is I'm going to take us to another spot in the sky just to see if, see the comet's pretty low. There's clouds down there, I'm sure. But let's just go up to Mizar if we can. Let's see if Mizar is still visible to us, shall we? Yes, we shall. So here we go. Telescope's moving. Let's look in the scope here and see if we can see stars going by at any point. If we do, okay. Well, that's telling us that we're getting some clarity. And this is actually a cool star. It's actually it's a double star. It's called Mizar. This is Mizar here, and then Alcor right next to it. And we will look at, let me show you. Okay, so
I remember when I was still young and pretty, I could see Mizar and Alcor both naked eye.
Yeah, actually, Alcor is the farther one. My mistake. Mizar is actually a double as well. And so this is Mizar here. Okay, and that's where we are looking, right here. Okay, see that?
Yep.
So that's Mizar and that's Alcor. And let's just take a little shot of that right now just to check it out. All right, 6 seconds at 5,000. And I want to, of course, hopefully we got the guide star. I think we got a guide star because, and what do we got here? Yeah, look at that. How beautiful. Yeah, it's a really beautiful star system. But we also want to pay attention to what's going on right here. And I want to try and, oops, sorry. I kind of screwed that up. There we go. So I want to take us back there for a second. So I'm going to pop over to our screen here. I'm actually going to bring this up into the view a little more. Okay, like this. And then I'm going to knock down the exposure time. Actually, knock down the ISO. If you knock down this ISO, then it gets much, much better in terms of noise in the system. So now, if you notice, you can see that there's more than meets the eye here. If I go into our focus mode and I just bring Mizar over a little bit. Okay, you can see it right there. This is Mizar. All right, and you can see that we're actually looking at a double star there. There's more than one star right in this view. See that? And so in order to look at that up close, we're going to knock down to, say, 400 at 5 seconds. Okay, and that should be able to show us the separation between these two.
Yeah, Mizar is one of those things. I guess whether I really was pretty when I was young is debatable, but uh, Mizar and Alcor were considered a good naked eye test of visual acuity.
Yeah.
Mizar is the middle star in the handle of the Big Dipper,
Yep.
and when you would look up our naked eye, if you had good vision, you could see Alcor right next to it.
Yeah.
And then when you looked at it with a telescope, you would see that Mizar itself is a double star.
Yep. And that's what we're seeing right here. This is Mizar and its companion, and then this is Alcor, I think, right here.
Yep.
So isn't that something else? Like to see that, that's beautiful. I like looking at double stars too. Double stars are gorgeous. Like if we bring in Mizar right here, you know, that's really pretty. I'm gonna actually check out if I find a slightly fainter star because I might. There's one over there. I was thinking that maybe what I'll do is check the focus, and I might be able to refine the focus a little bit. For those that know, I'm someone that likes to at least give you what you come here for. I want to make sure that things look focused and proper. So this star right here, right there. Okay, this star right here, I'm going to use as the focus star. When I do this close up, you'll see it right there in the middle of our focus setup here. There it is, and you can even see the companion star next to it, which is down here. Now I'm going to add the focus, and you'll see over here, for those just joining who have not joined us before, this is the telescope control system. This is the telescope computer setups area. This is the focus area, and then down here is the filter wheel setup, where I can actually use the filter wheel and put a different type of filter in front of the camera automatically and remotely. All right, so let's focus now. So I hit this button, and you'll see the image will bloat a little bit, and then you go the other way, and the image will get smaller and sharpen up. Okay, and then when it gets to that bottom area where it's the sharpest, it'll then go bloat the other direction. And then I will be able to kick it back the other way just enough to be in focus again. And you can tell when it's going to be in focus because you actually can see this little companion star over here much more clearly. And so now we just try to do our maneuvers here to focus it. You know what's funny? In astronomy, we spend more time trying to focus our images sometimes than taking the pictures. And for the research I used to do, I literally had to do some crazy stuff. I had to really try to calculate all kinds of parameters for stars, and I had to do it using some exacting mechanisms, and that's what we did. We had to do that endlessly sometimes. Let's take another photo, see what we get. 5 seconds at 400.
You did photometry, correct?
That's correct. And what photometry is, where you measure the counts of photons hitting a detector. Sounds really nutty, but that's exactly what it is. And using the photometry or the photometric results, you calculate how much air you're looking through. You calculate the angle to the horizon, and thus how much exact amount of air. Knowing the molecules in the air, you calculate something called extinction, because if your light is affected by how much air you're looking through, so you gotta get rid of that. You gotta negate it, and that's what we do. All right, so this is Mizar and Alcor here. There's Mizar there, the double star, and there's Alcor over here. We have some. These are nice images for as far as the telescope goes, because it shows what we call an airy disk. Right there, you see this little disk around that star. It shows the telescope has collimation has been done correctly, and it's even still a little bit too long in exposure, because I want to try and reduce the size of the stars. I'm making a point here, believe it or not, And now I'm down to half a second. And let's see what that does. Okay, if I can get what I want, the result. All right, so I do this and it'll pop right in. Okay, now you can see them a little better. That separation is pretty. That's beautiful, Daryl.
It is.
And this is white light too. And of course, Alcor is still out there. All right, and now when we look at Mizar again here, I'm going to now do another thing. I'm going to take now and I'm going to reduce the exposure yet some more. Okay, and I'm going to go down to a 20th of a second. Sounds good. Let's see what that gives us. It's going to give us kind of what we see on the screen here. Okay, and now popping right in. Okay, we see again. Now compare that to this. Okay, this is a previous exposure. And you think, wow, two big stars right near each other. But then you look at this and you're like, wait a minute, they don't look like two big stars near each other anymore. You know, they look like they're a little bit farther apart. And if we go even smaller, okay, there's a point. There's a point to all this. So let's go down to, I'm going to try a 60th of a second, all right? It'll be instant. Here it comes. Okay, and then we bring it in. All right. Oops. There we go. All right, so this is good. So now at a 60th of a second, you can see that there's a separation. Now, again, compare it to this, all right? And now you see this. All I've done is stop the amount of light coming in, and it's gone from stop down the amount of light coming in. So it's gone from these objects that look like they're extremely bright, okay? All right, that's over there. Okay, this is right. All right, extremely bright down to something that actually has a reasonable separation. Now, reduce the size of these objects down to one single tiny pixel in your mind. Okay, one tiny pixel, one element of one of these images. Look at the tiny little pixel. And then you have to go about 100 times or more smaller than that. That is actually what we see in the sky with stars. Stars are ever only little tiny points of light. You can't see diameters of stars. The only reason you see the diameters or the relative diameters here is because of their brightness and the fact that they're saturating the detector. Okay? Saturating the detector. Okay, Brandy. Good night. Thank you for stopping by. Really good to see you. And so when this is bright up here, that's actually just saturating the detector a little more than this one because it's a little more bright. But again, imagine one tiny pixel, smaller than about the size of maybe the very point of this arrow, okay? And imagine that being 100 times smaller, okay? That is the size of the actual starlight that you're seeing, and it's even smaller than that, like I said, because stars vary in distance and size. But stars are ever only points of light, and if we couldn't see the bloating caused by our eyes when we look at stars in the sky and by the atmosphere, we would think there are no stars in the sky, except for maybe the brightest ones. But because our eyes are so sensitive and because the atmosphere spreads a lot of this light, we see more stars. Paradoxically, up in space, when you look out at the Milky Way, yes, it looks gorgeous, but you're looking at it and it looks very different than the way it looks on the Earth. On the Earth, the stars are made to look bigger. Each star looks bigger because you've got this effect going on. Okay? The atmosphere makes the stars look like that. Up in space, they look like that, or less, right? So the Milky Way doesn't look as much like the Milky Way. But because there's no light pollution, if you can see the Milky Way without the light pollution, it looks much brighter because there's no light pollution. But it's less dense looking. It looks less like this. It looks more like clouds of knots of gas and dust. Because on the Earth, when you have something like this that you're looking at, it looks full and voluptuous, you know. But up in space, we don't get that. We get this. So it's just thought I'd run that by you guys just so you get an idea. So hopefully that makes sense to you. If you have any questions, let me know. And good night, Marianne. What's that, Daryl?
I could tell a story about that.
Why don't you, please? That sounds good.
Okay.
I want to hear it.
Early 1990s, I had the 8-inch Celestron set up in my front yard. There was a total lunar eclipse happening, and I was taking photographs of it.
Okay.
The moon that night was moving in Taurus. It was in or very near the Hyades. And when you look at the Hyades cluster, well, you see kind of a V shape with Aldebaran, the bright orange star, as the bull's eye.
Yeah.
In the telescope, there were lots of stars visible in the background as the moon slowly moved from west to east as it orbited the Earth.
Mm-hmm.
And again, it was in eclipse. Well, I noted that there was one star in particular that was going to be eclipsed by the moon in a matter of a few minutes, and I kept watching it. And the moon moves about its own diameter in the sky over the course of an hour. And so as the minutes went by, I could see the moon getting closer and closer to this one star. And I watched it very carefully at the very last second before it eclipsed it. And the limb of the moon passed the edge of the star. I would have expected the star to wink out instantly because, as you said, stars are actually point sources of light, with a very few exceptions. What fascinated me, though, was that the star did not wink out instantly. It dimmed. It stayed dimmed for, maybe a second or two, and then it went out. And I had to think about that, about what I had just seen. The conclusion I drew, I can't prove this, but I think is what happened, was the star was a so-called spectroscopic binary. That is, the two stars in this binary system are so close together, we cannot split them with an optical telescope. Generally, you split a spectroscopic binary by seeing the doubling of spectroscopic lines in a spectrometer. The moon eclipsed the star anyway. It didn't know any better. But what it did was it eclipsed one star, and then a second later it eclipsed the second star. Does that make sense?
Yeah, actually it does. It does, actually. I'm going to go move the dome, okay? So I'll be right back.
Okay.
All right.
I'll try to keep people entertained.
Oh, I know. I'm. You know what? You do a fine job. You always have, and I'm. Based on the comments I get from people, you are a fixture in SkyTour LiveStream. I'll be right back.
See ya. Anyway, hello. How is everybody tonight? You watch the sky enough, you see some strange things. I don't talk about it much, but UFOs, I'm not really interested in UFOs. I have managed to see a number of them over the years, though. I've been doing this for about 40 years now, and sometimes things just happen. I used to live in the highest city in the United States, up in the high country here in Colorado. Elevation was 10,200 feet in town, and I was up on the side of the hill. I was like the last guy on the east side of town, and I was at about 10.6 or 10.7. And, you do enough looking and you start seeing other things in the sky. I saw UFOs several times when I lived up in the Leadville area. It was pretty neat. There are stories of sometimes what people might call UFO being ball lightning up in the mountains. That it's called a piezoelectric effect. That compression of rock strata at depth would sometimes cause an electrical discharge, and you would get ball lightning. And sometimes they'd see those floating around in the mines. You know, you'd be in a tunnel in a mine, and here comes a piece of ball lightning floating at you. I might have seen something like that, but then more conventional so-called UFOs I've seen a few times also. But I don't really find, I don't find them that interesting that I go gaga over UFOs or anything. And Mark is back, so welcome back.
Oh, no, that's okay. I was I was listening to you like I was listening to a radio show. I just wanted to hear it. It was kind of cool.
Oh.
You know, you have a lot to say. You have a lot of knowledge, and I think it's pretty cool. you know. And
Well, I don't know what I saw those nights. I mean, I'm not saying I saw flying saucers. I
you know,
don't know what I saw, so by definition, I'd call them UFOs.
that's true. Unidentified. Oh, what's that? That's unidentified. Uh, yeah, this is. I told the telescope to go over to the moon, and hey, look, it went. Not bad. All right, let's just. The moon's getting lower to the horizon, so it's kind of fun to watch the neat anomalies that can happen to the moon when it's near the horizon. We're gonna reduce the exposure a little bit, get a little bit darker, and let's go into our focus fixture here. I like to check this out to make the moon as sharp as possible, because if we don't, then it's really not helpful. We got to make sure that we get the moon nice and sharp. See how that looks fuzzy? But you can actually see this is what we're talking about when it's near the horizon. Look how wavy it is. This wavy nature is just like, showing us that the moon is just really a mess air-wise. And I'm just doing some focus stuff here. See what we get.
We call that astronomical seeing.
That's correct, yeah.
SEEING. That's the turbulence in the atmosphere.
Yeah. And the alternative, the one that I used to do, I used to have to estimate the seeing and transparency every night for the observatory, where I was doing the parallax work. The parallax is the study of nearby stars. And I would have to put down on a scale of 1 to 5, just for purposes of understanding, what we might expect for bloated images of stars. I would actually have to put down an estimate of the transparency and the seeing. So the first thing you do when you get to the observatory is you spend some time outside examining the sky, especially where all your program stars are in the sky, and you figure out what the transparency and the seeing is going to be in that particular star's location. The transparency is basically how clear the atmosphere is, how clear the air is. Is there a lot of water vapor in the air? If there is, then you get like a hazy, humid day. Okay? If there isn't a lot of water vapor in the air, then you got an exceptionally clear day, and it's gorgeous. And we've seen that before here, as a matter of fact, in SkyTour LiveStream. And then we would do our program stars. We would actually take the images of the stars and we'd send them for special measuring, to measure the positions of the stars with a special computer that can actually find exactly where the center of the star image is on that image. And that was important to do. So let's take a picture here to be very quick. Hey, look at that. That looks pretty. Yeah, look at, and there's the crater Kepler right there. I'm sorry, Messier right there. And I actually, where is it? There it is. I have I get access to all the U.S. Geological Survey imagery, and this is Messier crater. I actually made this. I 3D printed this on our SLA machine. I might have showed you this last time. And you can see Messier crater. And I know it's a little bit off, but you know what I'm going to do? This is probably better to just do this. I am going to do this for now. Okay. So now you can see Messier crater, right? And it's a 3D print that's about, I'd say just over a 1/4 inch thick. You have every detail in here. You can see all the details. It's really incredible, And I really like how these come out on this printer. And so I go to the site and I actually will print these out. And I get the digital file down on my machine, and then I can proceed to, do what I have to do. I have to paint it. So I actually paint these to look like what we see in the moon. And that right there is this crater right here. All right. It's a double pit. It's a very shallow angle impactor, and first it hit the moon and then rebounded and bounced and lodged in the second pit, is my understanding anyway, because sometimes it still made these giant pits, and it was a low angle projectile that didn't hit with such energy that it distributed it evenly in all directions. When a meteor hits the moon, okay, one thing to understand is that when a meteor hits the moon, it actually strikes the moon with a lot of energy typically. And that's why when you look at most craters like these, by and large, these craters are round, okay? And no, they're not all the same depth, by the way. The depth varies. If you measure the base of the bottom of this crater and the bottom of this crater, you'll find that there's a vast difference between them. They're not even. It's an illusion created by the fact that you're so far away you can't see the difference, but it could differ by hundreds, if not 1,000 of feet or more. So the moon, okay, when impactors strike the moon, this hit right here could have been at a relatively shallow angle. It could have come in from the side. But it hits so hard and it hits with such energy that it's distributed in every direction evenly. Now, where have you seen that? Here on Earth. You've seen that when you skip a stone across the lake. You're throwing it at a very shallow angle, and everywhere it hits and bounces, it makes concentric rings out from that impact point, you see. The energy doesn't go in an ellipse, doesn't go and then go push forward and make an elliptical set of concentric chains. No, it only makes circular concentric chains where each impact was. And that's exactly the same mechanism that the moon has going for it. If it's a direct-on impact, then the craters are, of course, round. If it's a shallow impact, then the craters, if it's high-speed impact, are, again, round. Round craters are common for this very reason. It has to do with the way energy is distributed on impact, right? And the bigger the impact, well, the bigger the crater and the larger the scar, like this one over here. Okay, this was a major impact, all right? Now, it didn't have to hit straight down. It could have been at a glancing blow that might even have left the moon after that, for all we know. But the energy was distributed evenly in every direction here. Most likely, it embedded itself in the moon, probably struck the moon at some angle. But that's the kind of thing that happens on the moon. And, when we look at this stuff, I think that it's important to understand that energy of impact on the moon is what determines what the moon actually looks like. Okay. Daryl, did you have anything you wanted to say about lunar impacts at all?
Just talking about Messier. That's
Okay.
one of my favorite lunar features, and yeah, it really was an oblique impact, and it bounced, and you could see on the model you were showing, and when you were showing it in the view of the telescope a few minutes ago,
Yeah.
you could see that just like most impacts, are circular. What they leave are circular. Right there is Messier, and there's a bright ray coming out there from right to left.
That's right. It's
And
going down
that
to the
is like
lower
the
left there.
splash. That's the splash pattern of the ejecta. It all went out in one direction,
That's right.
or mostly in one direction, which is what we see.
Yeah.
And it's just really neat to look at.
It is. It's really pretty. And that's when, so you can see on this model, you can actually see. I did add the ejecta pattern there. You can see it coming out right here, going out. And it's actually in Messier, what you can't see in that image we took there. It's actually two bands of material that just blew out sideways like that, and that's what it looks like, you know. And it's really cool because you get to see it, well, just like it is on the moon. You know, it's a relatively open area. It's an area that occurred, or it's an area that a crater that occurred in a Maria. Okay, so it's actually, you can see that this area over here where it happened is actually somewhat open. All right, really impressive area. Just impressive.
Mark,
Yeah,
could you hold your model up again?
sure.
one more time.
Yeah, let me do that for you.
And
Let me
okay,
do it
there
too.
you go. The orientation. That is a close match, right about there.
Yeah,
That's a close match to the orientation that you're seeing of the actual
right.
craters and the ray pattern on the face of the
Yeah,
moon.
thanks, Daryl. That was a good point to make. Yeah, so you can see how that looks now. So if you imagine yourself in orbit around it, or orbiting the moon, this is what you'd see if you were closer. And in fact, several of the Apollo astronauts, the Apollo astronauts took photos of Messier. They did orbit Messier fairly close to the moon, and they took pictures that kind of were about this close, maybe a little bit closer actually, and really quite a fascinating little crater. you know. So these are 3D prints, and if anyone's interested in getting any of these 3D prints, we do sell them pretty much at cost. We'd like to give people their favorite craters on the moon. We think that's just so cool. We have all of them, actually.
There's another three of my favorites right there, right of
Yeah,
center.
yeah, right here. Oh
Nope,
well, this
farther
one.
over to the right. Yeah, that's the one I call the dumbbell, and it looks like there's one of the plates is falling off one end. There you
Yeah,
go.
yeah, right here.
Uh-huh. That's Theophilus,
Yeah,
Cyrillus, and then the third one on the other end of the handle, a little bit farther down. We only see the top two right now. Uh, no, yeah, there it is.
yeah,
At the bottom of the screen, that's Katerina, I think.
yeah,
Theophilus, Cyrillus, and Katerina.
yeah. These guys, 1, 2, 3.
Uh-huh.
Yeah, and here's another shallow impact right there. You can actually see the ejecta going that way. And as you know, before we talked about this, this was a shallow impact, but notice there's a gap before the ejecta starts. And why would that be? You know, well, that would be because in the initial impact, the impactor probably pushed a huge ridge of material as it struck, making like a brow ridge, and it shielded the area just beyond from getting struck with the ejecta that then came out in full force. It depends how it got shoveled, in the initial moments of impact. The other thing is, many of these craters, when they occurred, were, they didn't take place over minutes or several seconds. They took place in fractions of seconds. So, you're seeing a lot of effects that occurred that made the moon's surface almost act like a liquid. You've heard of liquefaction, and if you took what's called a shake table, and you filled this box on this table with sand, and then you put a toy car on top of the sand, it's certainly not going to sink in the sand, but you vibrate the shake table at a right frequency, and that car will sink like a boat and be sinking, and end up on the bottom of this sand vat. Okay, and that is liquefaction. Well, when a large asteroid or meteor strikes the moon, like this one, okay, or this one, okay, or this one, which is even higher energy, and you'll say, well, how do you know? Well, because look at the central peak. The central peak shows that there was a lot of energy of impact here. Same here. Okay. And this might have been higher energy, and the central peak may have been destroyed in the ensuing flooding of the basin that came about when the meteor punctured the moon and lava started to flow in here, and all because of the impact. It's you got to imagine that objects that are flying toward the moon at very, very high speed, many tens of thousands of kilometers an hour, when they strike the moon, they go from going that speed to zero. And we have to consider that all that energy of motion, called kinetic energy, and for those who want to know, that's 1/2 the mass times the velocity squared. That's the kinetic energy of an object. All of that gets converted into heat, because that's the only other thing they can do. And so all that energy of motion gets converted to heat, and that heat can be stupendous, and it can melt the surface instantly. and all the ejected material could be molten and melted pieces of rock from the moon, and then it scatters around the moon. Now we see, that molten material will act like a liquid for a period of time in the center of the crater that gets when the strike hits. So when we see a crater that has like these central peaks, I liken those, and you can think of them this way, as the bloop. What's the bloop? When you drop a pebble in water, it goes kabloop. And when it goes kabloop, the bloop part is when there's a central piece of the water that comes whoop up from the center. Now, if you froze that in time, doesn't that look just like a central peak? Well, there's your bloop. Okay? It's just when it happens in rock that has been liquefacted by impact, and the energy of the hit and the vibration of the strike can make the soil go into a liquefacted state. Then what will happen is it'll act like a liquid for a period of time, and that central peak will be that the crater gets gouged out is a gigantic hole first, and then that material comes rushing back in and hits in the center and collides and goes up, and by that time the liquefaction phase is done, and it freezes that way for all eternity. Okay, and that's what we're seeing here. So these are the bloops, and so I think that when you look at the moon the way we look at it, you have to look at it from the point of view that some craters have these bloops and some don't. Well, we recognize that some craters are what are called simple craters. This guy is a simple crater. This is a simple crater. That's a simple crater. It's just a hole where the impact energy was, the impactor was vaporized when it struck because it struck with such energy. It made a giant hole, and any spray that came out was either later covered by other spray from other craters that were made, or it didn't have a whole lot. Because you'll notice that we see rays on some craters, but not on every crater. And that's because of the terrain it's hitting and so forth. But the size of the crater is dependent on the size of the thing that hit. If a large thing hits at slow speed, then you can get a larger simple crater. And if a small thing hits at a very, very high speed, that can actually cause more damage than a bigger object moving slow. So, yeah, Raztaz, bloop, yeah, it's the bloop, bloop. So the moon's features and layout and the highs and the lows. These are the highlands down here. Okay, these are the lunar highlands down here. Okay, these areas are very high. And what do we say high? We mean relative to what we call the mean radius of the moon. The moon has a certain mean radius, and that radius is a certain value. It's one number, okay, like, just the kilometers, a couple thousand kilometers or whatever. I forget, the 3,000 kilometers roughly. And if a feature is above the mean radius, then it's going to be above that number. But it could also be below the mean radius. So what happens is they don't measure absolute values, that is, say absolute heights, altitudes. So if something is at the mean radius itself, then the radius, that the actual elevation of the object is given as 0. Okay, if it's at the mean radius of the moon. If it's a big hole in the moon, then it's negative. It's below the mean radius. And if it's higher, then it's given a positive value. So in the lunar highlands here, some of these numbers can be positive, but you can also get raised areas that are negative, because overall their altitude, even though they look like they're very high, are actually below the mean radius of the moon. And that's why we can get these inexplicably weird altitudes on some of these craters. You can have an entire crater which has this gigantic rim all be a negative value. Okay, how do I know that? Because I make these things in 3D, and when I get the 3D data, many times, if not every time, the crater and its rim, which is really, really high, are all negative. And what I do is I have to convert all those to higher values, all right, because the negative values mess up the 3D models. But don't worry about that stuff. The thing is that's interesting is that this gives us an idea of how high and low the different areas of the moon are. Also, you'll notice the different colors of the moon. We've talked about this before. When we look over here, okay, we're looking this area right here. It's like chocolate brown. It almost looks like it's chocolate brown. Every time I see it, I want to go eat some chocolate, actually. Right, but then right down next to it, we have this area here, and this is a gray Maria. This gray area here is just like a gray lava that has cooled on the surface of the moon. And then we have some other spots. Let's see here. We have some other spots where we actually have some really stark color differences. Okay, for instance, all right, if you want to look at a stark color difference, let's go over here. Look at that. Look at this little area here. What's that? That little white thing, and then we got this little area here. Why would this be like this? This looks like almost like maybe that might have been an impact over there. Maybe it was, and maybe this was a crater rim here. Okay, all right, crater rim. Let's see, let me get my hand to show up. A crater rim here, all right, and that crater rim had a central peak in it, and a subsequent impact flooded this part of the moon with lava, and buried the whole crater other than this edge of the rim and the possible top of the central peak. See, this tells us that the features on the moon happened in a certain order. Hey there, watch show TV. How are you? So I think that's really important. City Lights, hi. So I think that we want to consider how these things had formed on the moon, and this actually explains to us a lot about what the colors mean and so forth. The moon is actually really a stunning place, and I used to, I'll tell you right now, as an astronomer, we hate that thing. We don't want that. We don't like the moon. Why? It gets in our way. The light ruins our views. However, I will say this. Even though the light ruins our views, to see this right now in our view and in the sky like this is really, really pretty. And I can't help but think that this imagery right here is so stunning. I love these low angles of light. I mean, this is why I print them out and make 3D models. They're really just beautiful,
Mark?
Yes, sir.
Could you pan back up a little bit to where you referred to the chocolate and the gray area?
Sure.
And you see the demarcation line between the two of them there? Could you
Yeah.
possibly zoom in on that just a
I
little bit?
can, yeah, right here.
How sharp that difference is right there.
Yeah.
And it looks like the gray may have even overflowed a little bit into the brown area.
Yeah, because it looks like it went over this crater rim here and flowed down into this area. How would we know that can happen for sure? Well, there's a tool that I show you how to use and have done a lot of tutorials on, and it's called the LRO for Lunar Reconnaissance Orbiter, LRO Quick Map, one word. And it's run by the Arizona University, and you can actually draw a line from here to here and get the altitude information. It'll show you a graph showing all the ways that terrain moves. So we could see if this is actually higher and it just stopped there, or if this is lower and this spilled over into there. We can actually get that information. We can also just go to the USGS site and we can get this information, download the digital files, prepare them, print them in 3D, and then have it right in front of us too. It's another way to do it. And I've gotten so quick at that, I can download something and have it printing within about 10 minutes. And it used to take me about 2 hours to prep these things for printing, and now it just takes 10 minutes. That's a couple years, though, of working with the folks at the data center out there and talking to and trying to help them troubleshoot the stuff, the data, because sometimes the data was bad, but it's getting better. It's actually quite good now. But this looks really nice. And, when people think that the moon is like all gray, well, it certainly isn't. When we look at the moon, we actually can see that the moon actually is a bunch of different colors. Astronauts saw orange soil. Orange soil. And that's pretty crazy, huh? Orange soil. I want to try and just do one more focus here, because I think we're low to the horizon, so we'll do as best we can here. But I think that that's about it. We're not going to get much better than that, especially tonight. But this, the phase of the moon right here this is first quarter. And what that means is the moon is 1/4 of the way around the Earth. Okay? And there's someone in the chat that's going to really like to hear this answer. But if it's noontime and the moon is just rising, okay, noontime and the moon is just rising, this is the phase you're going to see. All right? And if the sun is setting and the moon is just rising, then it's going to be full. Right? And if it's somewhere between noon and the time that the sun sets, say halfway between, then it's going to be somewhere between first quarter here and full moon. So, about halfway between, and Tara knows what I'm talking about because she asked the question earlier, is going to be the gibbous moon, which is the answer that Tara seeks. All right? She asked the question, what's the phase of the moon at 3 o'clock when the moon rises at 3 o'clock? Oh, that was weird. Did you see that? We just saw something right here that came and went, a red flash. And so if it's 3 o'clock in the afternoon and the moon rises, what is the phase? That was on a test that she had in astronomy, and she got that answer wrong. But Daryl, right? The gibbous moon rises somewhere between the first quarter moon and the full moon.
Yep.
And that would be probably, say, 3 o'clock if you had to go between noon and 6 or so. And so that's a gibbous moon, waxing gibbous moon, as a matter of fact.
Yep. Full moon also being second quarter moon.
That's right.
Yep. A new moon will rise and set with the sun. A first quarter moon will rise at noon, be due south at sunset, and it will set at midnight.
Yep.
A second quarter or full moon will rise at sunset. It will be due south at midnight, and it will set at sunrise. A third quarter moon will rise at midnight, be due south at sunrise. It'll look just like a first quarter moon, except it'll be facing left instead of right.
That's right.
And it will set at noon. And the fourth quarter moon, well, that's back to the new moon, and it will rise and set with the sun.
Yeah.
The moon between new and first quarter is crescent. The moon between first and second or full is gibbous, waxing gibbous, as you say. It's getting bigger day by day.
Mm-hmm.
After full, it will be waning gibbous until third quarter, at which time it becomes a waning crescent.
That's right. And that will be on the test. So make sure you study that. I'm kidding. I want to say hi to a Neutrino and Nildeti Karaya. How are you? Welcome to SkyTour LiveStream. I know that Neutrino has been here before, but Nildeti has not. Let's see here. Okay. I'm just going to restart something. I'm just checking my stream health here. Alright. It looks like we're still going. If anyone noticed any starts or stops in the stream, let me know. Keith from P&K Space Imaging was saying that the streams, when he was streaming, was actually doing some stuttering. And I just came in and saw there was some kind of error, but I don't think it actually interrupted the stream. but you'll let me know, I'm sure. Okay, so that's the moon there, and we have a bunch of clouds around, so it's making it hard to decide what to do here. I can't show you the comet anymore because that's it's going to be much lower in the sky, and it's also going to be enveloped in these clouds that we have that we don't want. The true bane of astronomers is the clouds. That's the true bane. Now these are white light photos, by the way. If we want to change that, let's do some playing around. Now you'll see the this is called a narrowband filter, okay, and it's a filter that is allowing specific thin wavelengths, thin slices of light coming in from very specific locations in the spectrum, locations that enhance stellar nurseries that have what's called hydrogen alpha at the 656 nanometer location, oxygen 3, which is bluish cyan color, and sulfur 2, and these will allow us to image nebulas much better when we look at them. We have another one that's also a narrowband filter, but this next one, you'll see it move in now, slightly wider narrowband filter, and so that was something that actually we actually use for mostly focusing on and taking pictures of nebulae. Okay, not usually the moon. And then we have a spectral one here. This is kind of spectral. You can actually see the spectrum of the moon. We did this on the comet, and you actually saw the definitive differences in the materials in the comet's nucleus. However, we have a unit here that is going to allow us to pretty much excuse me, look at the spectra and identify exactly what's in the spectrum. The unit, I got it from France, and it's here. I've used it. It is spectacular. Looking at just a regular fluorescent light, I can see no less than like 5 frequency lines that make up the fluorescent light. It's really beautiful. Actually, there's way more than that, but there's like 5 primaries. It's really gorgeous. All right, and this is sort of a shotgun approach. This guy here, this next one, this 4th location in our filter wheel has just a black disc, and we need that because when we look at black discs, then we can actually act as if the telescope's covered and take pictures that way, and that's a very important aspect of taking photos to then stack later. Okay, so here is the white light photo. Let's actually let's take a slightly longer shot, and let's actually go over and see if we can focus on this guy, the Kepler. Should be right about there. So we're going to take a 50th of a second at 160, but I'm actually go down to 50 ASA. I want it to be as fine as possible. The lower the ISO number, the less we'll see noise, and then we can take a slightly longer exposure to take advantage of that. All right, so we'll do a 20th of a second at 50 ISO, and here we go. All right, and now here's what we got. Let's see what it looks like. All right, that looks a little better. We can see Messier over here. I keep calling it Kepler. I don't know why. I guess I'm nuts. I just keep saying that. All right. Yeah, and it's beautiful. And that division Daryl was talking about here. Here's another one over here. This is really interesting because if you notice, you'll see this actually has a dark edge to it. I want to really focus at some point and see what's going on in here. Now, one thing we can do with that spectral system I was telling you about, the moon is quite low right now, is we can look at the reflected light from the moon and take a little section of that light. And what do you think we'll see for a spectrum when we look at it? Anybody have any guesses out there in the chat? Okay, what were we going to see? If we look at this and we want to look at the light, okay, you see the darkened light areas on the moon. What do you think we'll see when we look at the spectrum of the light coming to us? I can tell you right now, without even having seen the spectrum, what it will look like. And you might say, wow, you must be smart. No, I'm not smart. I'm just putting together some of the science of what we're seeing here. So throw that around and have a few guesses, and I'll be looking. Okay. Yeah, City Lights. Yeah, he says that space smells like burnt steak. That actually smells like the moon tastes like steak. Yeah, well, the moon is actually made of tiny, tiny particles of fragmented glass particles that were cooled very quickly in the absence of the atmosphere, and they're very sharp. And the way you know, Ronald, is that when astronauts go for spacewalks and they come into the ISS after doing spacewalks, they take off their spacesuits, and there's a smell that has permeated the spacesuit from the outside, and that smell is the smell of space. Some people say it smells sort of like gunpowder. Some say burnt steak. There's about 3 or 4 other things they think it smells like. And if you really want to know, okay, City Lights, good guess. Thanks. That's an excellent guess. And Anahata, good guess. If you really want to know what it smells like, you can actually buy Fleur de Space. You can actually buy a perfume or a cologne, depending on how you want to look at it, that is actually the smell of space. And I actually want to get one. I actually want to get that and just like, oh, what's that cologne? It's Fleur de Space. You know, say it like that. You know, like, oh, what's that? It's the stink of space. You know, well, you smell like a muzzle of a gun. Okay, or you smell like burnt steak. Ugh, you know. And by the way, there's a reason for that smell. And some people were saying that it's the interaction on the spacesuits with the solar energy hitting it. That's actually a very good thinking. But that's actually not what was causing that. Okay, what causes this is the fact that our galaxy and other galaxies are actually bathed in these compounds, and they're thin. That's to say, they're low density, and these compounds that the galaxy's bathed in, we're going through with the Earth and the Sun. So that could be responsible to impart. It could be responsible for imparting the smell to the spacesuits. You know.
As I recall, the Apollo astronauts reported that when they came back in from their lunar egress, they came back into the landing module that they brought lunar dust in with them, covering their spacesuits, and they said it smelled like gunpowder.
Yeah. Yeah. And you know, I just want to say, when I asked folks like, what do you think the spectrum of the moon would look like? Someone who was Anahata said a lot of blue, and City Light said maybe sodium and hydrogen. Very interesting, but you have to understand, and those guesses are not bad guesses, okay? But what's really happening is when we're looking at the moon, we're actually seeing it as reflected light of something else, right? And that's the reflected light of the sun. So when we look at the moon, we'll actually see the very specific spectrum of our sun, minus areas where the lunar soil has absorbed some of the radiation and energies at certain frequencies in the solar spectrum. And if you want to know what's on the moon in those locations, you can actually take a spectrum of one little segment of the moon, subtract the sun's spectrum from it, and the only lines left are going to be the differences between the two. And those differences are going to be the lines of things like helium-3 and titanium and other materials that are specifically in the lunar surface. Okay, that's really interesting, and we're going to try and do some of that when we get the spectrometer up and running. We'll have some fun. And again, the light tells us so many things, because that's really all we have, to look at. But I want to thank you for your guesses. You guys are wonderful. But again, we see what we call the Fraunhofer spectrum, which is a specific spectrum of the sun with all these many lines in it that correspond to areas in the sun where there's other elements from the periodic table that the sun was made with when it was first made. And here's another little thing which you may or may not know. When you look at the sun, it's this big giant ball in the sky, right? It's easy to think that entire big giant ball is radiating all of the energy that's falling on the Earth. But it's not. Okay? In fact, the big giant ball is composed of an outside, the area you see of the sun called the photosphere, and then it has other layers inside. But those layers are also not responsible for generating the energy that warms this planet. Okay, the only thing that's doing that is an area in the core, one little area in the core, the sphere all around the core that makes up the core. That core, where it's hot enough to fuse hydrogen into helium, specifically deuterium to helium-4, an isotope of helium. That core location in our sun is the only place where the energy is generated that has this ripple effect all the way through the star. Okay? And that ripple effect creates plasma all the way through the star, meaning it rips the atoms apart. All you get are protons and a bunch of separate electrons, right? All moving around, and that's plasma. The plasma follows the lines of the sun's magnetic field. You see them leap out and make these prominences from the sun from time to time, these loops and streamers and beautiful artifacts on the sun. These are protons and electrons that are glowing because they're plasma. And when it gets loosed from the sun and heads toward us, then we have what's called a coronal mass ejection, when there's a big flare. And every day, the energy coming to us from the sun is streaming with it high energy protons and electrons that are all charged. Protons are charged in what charge? Positive. And electrons are charged with what? Negative. And they're spraying out from the sun in all directions, 360 degrees and all around, up and down, all throughout the sun, a full-blown 3D emanation of all these particles. Every day of its life, every day. And so much so that we can calculate the loss of the mass of the sun based on this radiation pressure pushing out stuff. And when protons and electrons are leaving the sun, there is a mass loss calculation we can do for stars like the sun or bigger stars. Mass loss can be huge. Mass loss can be almost non-existent. But our sun, it's kind of, just below average. Big stars have a lot of mass loss depending on what type they are. So anyway, the really cool thing is when we look at the sun, only that central core is fusing hydrogen to helium, and only that central core is making energy that warms this planet. And here's something else that you may not know. When a photon is emitted inside, a high energy photon, after fusion, you get photons, you get other radiation that's emitted. How long does it take that photon to get out of the sun? It bounces around a lot, okay? Because it's being redirected. It's getting absorbed and re-emitted, Sooner or later, it gets out, So how long does it take for a photon to get out of the sun?
Long time.
Well spoken. The
I don't mean to steal the thunder of people in chat. It takes like hundreds of thousands of years just to move from the center to the face of the sun, doesn't it?
It does indeed. And in fact, when in some stars, it could take almost 1,000,000 years in some stars. Okay, but in ours, it takes 100,000 or more years for that photon of energy to get out of the center of the sun and make it all the way here. And once it gets to the surface of the sun and gets liberated, it only takes 8 minutes to get here. All the rest of that time, the overall vast majority of time it takes, is to get out of the sun. You know. Now, again, it depends on the type of star. There could be small stars where that doesn't take but a fraction of time to get out, and then there's stars that are so big that it could take beyond thousands of human lifetimes to get out, hundreds of thousands of human lifetimes to get out. And one figure topped over 1,000,000 years for a photon of energy to get out of the sun. Not our sun, but a larger star. Because there's a lot of collisions you can imagine going on between a emitted photon. It's going to be emitted, absorbed by something higher energy. It's going to kick energy states of another thing. The atoms it hits are going to absorb it and re-emit it. It's like it's going to be bouncing all the way around. And that happens a lot. I remember trying to calculate how long it takes for photons to reach the photosphere to get out of the sun, just the sun, and the times were staggering, and I just couldn't believe them. I thought I was wrong. I think it was on one of my astronomy exams at one point, and the time was stupendous, you know. And I understood it after we started building stellar models. We actually, to get the degree, we had to actually build a star. We built a star, and that star was, on the computer, of course, but we built the star. Oh, look at that. I got here just in time. See some clouds come in. That's cool.
Yep.
We built the star to actually see if we could get the star to, or get the star that we built to actually work correctly from the core all the way outside. My star worked, of course. Some people's stars just blew up. And other people's stars, they just never got off the ground. It happens. But there's you got so many different things going on in the star, and we did this from a book that I still have here and I still reference. It's called Stellar Atmospheres, and the book was by Eva Novotny, and I can't imagine who would want to write a book about stellar atmospheres. I guess if you're writing a textbook that's going to influence decades of astronomy to come, I think that's a good enough reason. I admit I wrote my book for the reason that I'd like to see colleges and universities use my book as one of these extra reading sources. Because these extra reading sources, or additional reading sources, are really quite amazing. Some of them really gave me more information than the actual textbook, because the textbooks are written dry. Okay, I have humor in there. I make things fun. I think that's what you got to do. Yeah. So right now, the moon, I think it's going to be more. I'm trying to see what. Let me just take a photo and see what we got. Well, there's our clouds again. Yeah, it's you can see the moon is now getting a little orangey, because again we're doing this in visible light. It's actually getting right near the horizon, and I gotta check to see which way the telescope is. I know the telescope's gonna be fine, but I just want to see where it's pointing, because I would like to make sure that Yeah, see, the telescope's doing its thing. Okay, it's fine. Actually, I'm going to show you something while I'm here. The moon's looking gorgeous in this orange. It's sort of like really, really ethereal. I kind of like it. Now, let me go back to here. Okay. And let's do this. All right, and then let's do this. Let's go look at here, and now you'll see that, and this is the actual view. This setting you're seeing, that is my house. That is the property. This is the observatory, the remote observatory out there, and this is the view we have. It's really quite a good view, and we have a Milky Way that's not quite this bright, but we do have Milky Way. It's a beautiful Milky Way. But we have clouds out there tonight, and we're not going to be able to see much. And Jupiter and Saturn are not going to be very nice. I thought maybe it'd be good to check them out, but they're just not all that good tonight. But I do, we did do a NEOWISE earlier in the evening, and now we've got the moon to end the evening. And it's just, I thought maybe a pretty way to go tonight, because we actually, it's really looking pretty. And what I'd like to do is, I want to see the moon all the way until we start to see trees. I thought that might be kind of cool. So it's going to be getting pretty low here soon.
Or clouds.
Or clouds, yeah, that's right. So if you guys like SkyTour LiveStream, if you haven't subscribed yet, please do, will you? Because I know that people really enjoy coming here. They enjoy hearing about objects in the sky. They enjoy listening to Daryl's stories and his wonderful astronomy knowledge, along with some of the stuff I say. And I just think it'd be kind of nice if you guys stick around. So please do subscribe, hit that like button, and hang out with us. We have a wonderful community here. If you look at it in the chat, there's a lot of blue wrenches. Those are the mods. So they will make sure that the information gets to me. If I don't see a question that you ask, one of them can let me know. Daryl's also looking in there, and it helps us all, very much. But I really hope that you guys are having a good time here at SkyTour LiveStream. We're growing in leaps and bounds. We had an unprecedented number of subscribers join us in the last month. We had almost 750 new subscribers. And depending on our stream, it's been really hard to actually try and answer questions because they go by so quickly. And even with 2 people looking at them besides me, we still didn't get all of them. But that's just what happens sometimes. Oh no, come on. We have clouds down by the moon. I can't see my moon. But you know what I'll do? Let's see if it's still available if we do a longer exposure. What do you say? Let's try 4 seconds and I'll try and increase the ISO. Okay. 1600 at 4 seconds. Here we go. We are getting our moon back. Look at that. Oh, that's kind of looking cool, huh? I'm gonna be a werewolf here. That's neat.
I saw the coolest moon up in the mountains once, years and years ago.
Did you?
The moon had risen over in the southeast, and there was a solid bank of clouds, but it was the clouds were hanging below the moon, and they did not come up and cover it. And through the telescope, it was through that old red telescope of mine, it looked just like the moon was over ocean waves.
Really?
That
Oh, that's nice.
At a magnified view, you could see the top of the cloud bank, and they were just in constant motion, and it looked just like waves breaking under the moon.
Okay.
It was really pretty.
Wow. And that's actually a good point. When you look at the moon, a number of things can happen. You see, people, they look at the moon and they see they can't see the air between us and the moon, of course, or us in the upper atmosphere, and then of course the vast vacuum to the moon. So they tend to think that the air is all homogeneous or evenly distributed and the same density and temperature. But the air is just as varied as the ocean water, and sometimes more so. So you can have areas where you're going through cool layers and warm layers and hot layers, other types of layers. And the thing that's interesting is this can lead to some really dramatic and very strange effects when looking at the moon. For instance, we can see what look like waves moving across the moon. And there are people that say, look, it's the lunar wave. It's proof. Oh, that's pretty cool. This is Tara suggested that I take this picture. And that did come out pretty cool, Tara. Look at that. That's almost an art piece. And these waves that we see moving across the moon are like linear lines that seem to just drift across the moon. And what that really is not proof that the moon is a hologram, okay? But it's actually the warm contrail air left behind by a passing jet, maybe even minutes earlier, where the jet might have passed out of shot, not even near the moon, but that air drifts over the moon, and it drifts right over the face of the moon, and you'll see a ripple cross over the moon. And people will say, look, there's a glitch in the matrix. Well, in fact, it's just the contrail warm air. And that's something that is really, I mean, it's obvious to me, but for other people, I recognize that things aren't as cut and dry. So I try to have patience to explain to people what I believe it is. But when people get on YouTube and they start crowing about this, if you know what I mean, they end up saying things that just are patently false. And they're not doing you any kind of good. They're actually doing you a vast disservice by trying to pretend that some of these things are actually an actual wave moving across the moon. It's really not. It's really not a good thing. And I'd like to see that stuff go by the wayside and get, pounded out of the psyches of the people that are just so convinced of this stuff.
Well, that's an indictment against education in the schools nowadays.
For sure.
You remind me of an infamous video on YouTube years ago. Some woman was using a spray nozzle on her garden hose.
Oh gosh, yeah.
And it was a sunny day, and
Yeah.
she saw the rainbow in the mist from the spray nozzle.
Yep.
And she was absolutely convinced it was some sort of government conspiracy. They were putting something in her water. Hello, David Schmidt.
Hey, David. Yeah, and she's right. They did. You know what she needs to do? She needs to stop drinking water.
Yeah.
Yeah. No, I mean it. She has to stop drinking water immediately.
Vodka's better anyway.
Sometimes I talk till I'm blue in the face, guys, and I realize that, some people just don't have a science background to understand, and for those people, I want to help. I want to teach. I want to make sure that they understand. I want to be the outreach person. I want to help them learn. But then there's other people that they stick to their convictions because they get more attention that way. And they also drag innocent people into their psychotic behavior. And then these innocent people think that weird things are afoot and go, I mean, what, is there really a wave? Is the moon really a hologram? And as Daryl said, if they were better educated in science, then maybe they wouldn't even consider that. But we have to understand that science in our country is not the only problem. It's the YouTube, you know, it's YouTube. YouTube, videos tend to show people in certain lights, and they tend to show certain things in a way that makes them look like experts. I've seen videos where purported to be like this woman who's a PhD in physics, no less. Oh, a PhD in physics. I guess she knows her stuff. No, she doesn't. She doesn't know her stuff. In fact, she is so wrong about what she's trying to say. I'm trying to remember her name too, because I don't mind. I've challenged her publicly before. And what is her name? If it's somebody you know, this throw that out there. It's related to the flat Earth people as well, because they're also they use her as like proof, and she is so dead wrong. She says she's done research when it turns out she hasn't done research. She's thought about something and thinks it does this, and her research is the equivalent to going to a YouTube video done by someone else. If you're going to do science, you do science. And what does it mean? It means you need to create a hypothesis, an idea. Then you have to test that hypothesis. You have to gather data that proves your hypothesis. And then you have to pass your data on to another independent group who can repeat your same experiment and your experimental setup and get the results you did and interpret them the same way you did. That's science. That's what they do when they find exoplanets. That's what they do. They actually send the data to someone else who confirms the data, and then they use a secondary and tertiary method to prove from different angles that yes, that's an exoplanet there. Things like that. And that is what happens, thankfully, still in real science arenas. In the pseudoscience arenas, then YouTube is king. Anything you say on YouTube can be considered science for the day. Hi, I'm scientist for the day. Yay, I've got a theory. Earth is flat. Yeah. Oh, wow. Is it? Yeah, it's just straight everywhere you look, so it's got to be flat. Yeah. As if.
Yeah. Mark, I am running out of steam here. Would you excuse me for the evening, please?
Daryl, absolutely. I was just going to wait for the moon set, but you know something? Before the moon sets, we're going to have Daryl set. Okay?
There you go.
Okay, so let's say goodnight to Daryl as we now witness the Daryl set before the moon set.
Well, okay, it won't be as spectacular, but
how do you know?
well, you better not be peeking through my curtains. That's all I'll have to say.
You know what? Never entered my mind. Never entered my mind. Okay, my friend, thank you so much for coming along.
Thank you for having me, and
of course.
It's fun to be here tonight. And good night, everybody.
Yeah. Okay, Daryl. You have a good night. All right.
All righty. Take care.
See you later, buddy. Bye bye.
Bye bye.
All right. So yeah. So I want to, like I said, and show the love for Daryl too. Give this a thumbs up. It's not just for me. SkyTour LiveStream is me, Daryl, and Amanda. So. It started out as me, and honestly, with everything that they've all contributed, I can't say that this is all me anymore, not even slightly. I owe them a great deal, and I will never take that away from them. That's our comet picture we took earlier, and what I'd like to do now is to take image of the moon while it's near the horizon with the other camera that's up on top. And let's go down to, this might be a little bright, but let's see if I can, let's go to a 160. We'll just do this. Let's see what we get. And not 8 seconds. Let's do 4 seconds. Just try it. Probably going to be bright, but I want to see some of the clouds around it. So, and we'll go back to this while we're waiting. No, don't have to wait. Ooh, look at that. Look at how beautiful red that is. And there's this first tree. See it right there? Yeah, there we go. Okay. Now, what we're getting at here is when we look at the sunset looks red too, doesn't it? Well, it looks red for the same reason that the moon set looks red. The sun's light is white. In space, the light of the sun is white. But on Earth, we see it as a little bit of a yellowy color. And so when you draw the sun as a kid, you say, the sun's yellow. Yay. You put in your yellow crayon. Hey, that's the sun. Okay. We did have white crayons, remember that? But the fact was that paper was white, so it didn't really help us much. So that's one reason the sun was drawn as yellow, but also because it looks slightly yellow is why we do that. But that slightly yellow color is due to the fact that some of the sun's light that's coming to us, whether from the reflection off the moon or from the sun directly, is encountering more air between us and the edge of the atmosphere that's way out there in that direction. When we look out here in this direction, out there in that direction, right there in that image, between us and the moon is, of course, 240,000 miles. But we don't just have 90 miles of atmosphere. We have substantially more because it's at a lower angle. It's 90 miles if it's this way, but if you're at an angle like this, it has to go out more. That's an even longer line of atmosphere we're looking through. And the more atmosphere that the light goes through, the more of the blue light, the higher energy light that comes from the sun and from the reflected sunlight off the moon, the more that blue light gets scattered and sent in all directions. That's why if you take a time exposure of the moon, a long exposure at wide angle, the sky around the moon looks blue. Okay? It's for the same reason. It's called Rayleigh scattering, and it's the high energy part of the spectrum getting scattered. The more light you go through, the redder it looks. So if our atmosphere was twice as dense, okay, what would this image look like? The moon would look like a sunset. It would be blood red. Okay? When you have a night where you have lots and lots of water vapor in the sky, the sky will redden the moon so much that it could look surreal if there's a lot of water vapor in the sky, because water molecules also cause reddening as well. But this is cool. Now you see where the tree is, right? See where the tree is? You see where it is? Here is the moon. There's the tree. Now I'm going to do another photo, and again it's going to be another 4 seconds at 160 ISO, and you'll notice where the tree is now. Look at that. All right, so we went from here, trying to get it to, there it is, like from here to here, and so it won't be long before the moon now enters the trees. So I think that's pretty cool. It's neat to look and watch. It just shows I can talk a lot, So, in any case, like I said, now if you want to let me just take a picture of it so we can actually see it without any overexposure. Let me drop it down. Let's go down to say 50th of a second at 100 ISO. It'll be a very fast shot. There we go. Look at that. So now that's what it looks like in the sky right now. All right, and it's actually pretty dim. Now if we actually not dim, but it's not in good shape to actually view it. So if we go up and we go to say 320, and let's fling that out instead of at a 50th. let's go up to say instead of 4 seconds, let's go to 8 seconds. Right, at 320. So it's going to be a brighter image, and we're going to see not only the tree here, but we're going to see this will be way overexposed. But let's see what else. We'll see if we can see some stars. Yeah, look at that. Isn't that pretty? That's of course just a secondary reflection. That is happens to be a star. And what star, you might ask? Let's go find out. So if we go look here, let me see if I can get the stars. There we are. See that when the moon's in there, it does cause a problem. All right, so we're probably talking about this star right here. Yeah, that's right. It could be that star. Oh, no, wait, it's not. It's this guy right here. Sorry. Okay, that's Mu Libra. Okay, it's actually a double star. The constellation Libra. And if we zoom in, you'll actually see it. There it is. Okay, and there it is. See, it's sort of down there. That's pretty cool. What a pretty shot, huh? That's really pretty. That's actually worth seeing it. That's worth seeing. Let's see if I do this, right? Yeah, that's worth seeing all the way exposed. I like that. That looks gorgeous. You know, if you guys are asking any questions, incidentally, and I didn't see it, I'm so sorry. I apologize for that. I'm trying to get to everything. Can't get to them all. But then again, sometimes I do miss them. Well, let's get out of here and let's do another shot. This will be, again, 8 seconds at 320. And let's check out, let's set this to this here. All right. Okay. I can see that trees are a little blurry. That's because they are in motion. We got a little wind out there. Yeah. And if we go back to our actual view of the moon, and right now we don't have any trees blocking it, that I can tell. But they will show up probably right about here, coming up into the view, just a little bit. And as far as the telescope is actually, you're probably not going to be able to tell what it's doing there, but I'm going to show you anyway. Let's just go over here. All right. And let's turn this on right here. Okay, that's what I wanted to show you, and let me just bring this up. Okay, so in the observatory, this is the barrel of the telescope here, and it's aiming pretty low on the horizon. The camera is here, and also this is the right here. This guy, let me show you here. This guy right here is the filter wheel. Then behind it is the camera. All right. The camera that we're using to shoot the wide-angle shots is, you can't see it. It's on top of the telescope out here. This is part of the guide scope assembly up here. There's a lot going on here. This is a rather professional setup, so it looks really pretty. And let's bring this down out of the way. And before long, we'll actually see tree branches, and they'll be silhouetted against the moon, and they'll actually be quite obvious. Let's just see if we can see anything here by doing this and overexposing just a little bit. Actually, I don't want to go to 20 seconds. You know what I want to do? I want to raise the ISO. So we'll go from 0.6 seconds, raise the ISO way up. That's what I wanted to show you. Okay, and then I will do this and bring it over a little bit. All right. And now if you look on the screen, what do you see? You see we have this side here. Now, how many think that's the dark side of the moon? Actually, it's the side of the moon that always faces us. But because it's only the moon is in first quarter phase, a fourth of the way around our planet, always facing us, this side that we always see isn't lit up yet. But we're very familiar with that side, and we're very familiar with what we see on that side, because when we actually look at the objects here, I'm going to just take a 2.5 second photo of this here and bring it in. Okay. And set it right. And I know you're saying, what the heck is that? If we zoom in, and this is the side that we are waiting for it to be illuminated. When it's gibbous, this is actually going to be illuminated to like here. Okay. And then when it's full, of course, it'll be the whole thing. There's a star. So we're looking at, you can see if it wasn't as low to the horizon, we can actually see probably Aristarchus, which is here. It's a fairly bright crater, one of the brightest craters on the moon. And it is it's a crater that's actually so bright. It's actually one of the brightest craters on the moon, the brightest rays of any the craters, and that happened because Aristarchus has a fairly young impact, only about 400 million years ago, and that white spray out of the crater is actually not had enough time to interact with the really harsh radiation from the sun, so it hasn't had a chance. We got some clouds coming. It hasn't had a chance to darken that material, but it can and will darken that material. Whoops. All right, let me come back down. All right, you can see some light clouds moving across the face here. All right, let's go. I'm going to come down from 2.5 seconds. Here we go. Now you see those clouds. Now we're at 1/10 of a second. Yeah. Thanks for hanging with us. You know, I know that it's maybe not as exciting as some of the other things that we've seen, but you know what? We're still having fun, and we're still checking out the moon right to when it's going to end up setting. It's all right. I appreciate you hanging here. Let's go back to our wide-angle shot and check it out now. Let's do another 8 seconds at 320, and the moon is probably going to be about here. Not quite. It's going to be probably right around. Oh, we'll see. There we are. Okay, so now the moon is starting to enter the trees as viewed from the telescope. So we come back here, and you'll say, hey, let's go find the trees. And we have to, there's one thing to notice, and that is that, okay, this haze here, these are the branches. Right here, these are the branches. And I don't want to refocus the telescope, but we could refocus the telescope to show just these branches. So it is down in the trees right here. And if we were to, let's see, no, let's see if we go the other way here. Increase. I'm trying to see if we can capture something here. Probably not. We need to actually, yeah, see, it would take a while. And like I said, I don't want to focus and go all the way in to focus again, because those branches are only about 75 to 80 feet away, and we're focusing on the moon that's 240,000 miles away. But in any case, this is our wonderful moon for tonight, and first quarter moon. You enjoyed it here first, and I wanted you to see the color. The color is really important to see how that color changes as the moon gets lower to the horizon. And of course, through more air, it's more turbulent, and the image is less stable. And that's with an atmosphere that is 90 times thinner than Venus. So would you be able to see a moon in the Venusian atmosphere? The answer is No, you wouldn't. How about in the Martian atmosphere? The Martian atmosphere is a small fraction of our atmosphere, so the moon would be very, very sharp and clear through the Martian atmosphere. But even with the Martian dust storms, where there's particles high in the air, that'd be like a bad water vapor day here. All right, guys. I had a great time with you tonight. Thank you so much for coming out and enjoying SkyTour LiveStream, our crazy moon, and this one crazy astronomer. I just enjoy your company. And I know Daryl, of course, is now probably snoring like a champ. But to be honest, I can understand. It's tiring. But thank you for joining me. And I will see you on the flip-flop. And we will be back with another stream very soon. Next clear night, as a matter of fact. If it's clear tomorrow, I'll see you tomorrow. All right, guys? So remember, go outside and always keep looking up. Good night, my friends. We'll see you tomorrow. Maybe. Bye-bye.